Today we'll focus more on the chemical reactions of alkenes. Notice starting from the first one, the ones which we already learned will take less amount of time to discuss. Check out. For example, catalytic hydrogenation of alkenes. We have done this as a part of preparation of alkanes. You know that when you react with H2 in the presence of nickel, we can have this as alkene. You all you need to recall is the alternative reagent. Alternative reagents. Alternative reagents is H2 added with either nickel, platinum, palladium, or palladium carbonated form, or we can simply take Rane nickel, or we can take something called Wilkinson's catalyst. Wilkinson's catalyst, which is rhodium triphenyl chloride, okay, like this plus H2. So all these reagents, they will make syn addition on the double bond and give you alkenes. Next, this is most of alkenes. Okay, one second. Right. The first of a kind we will notice is hydrohalogenation reaction. Hydrohalogenation is addition of HX. As you add HX, pi bond will take H plus from here, X minus gets added here. That's the overall reaction. Or the other way around can happen. Pi bond can get added H plus from here, X minus can get added here. Okay. So if you notice the mechanism step by step, first step of the mechanism is like this. The pi bond will take H plus present in the solution to convert this into either this carbocation adding hydrogen here, or it will add hydrogen here with this carbocation. And you can clearly notice that we are getting a 1 degree carbocation here and a 2 degree carbocation here. And 2 degree carbocation is more stable. This is more stable here, correct? And once you get that here, see, first of all, you need to realize this also that when H and X is breaking, so it is the delta positive charge and delta negative charge which is there on it, because of which this X minus will break. So that's how you can get X minus out here. And once you get this X minus out, let me put this as intermediate 1 and intermediate 2. Since this is more stable intermediate, I am doing the reaction based on intermediate 2. So you have got this carbocation here. On that, X minus is going to attack. As the X minus attacks here, this is a very fast reaction. In fact, the first step is always the rate determining step, and this is the slow reaction because you are generating an unstable intermediate. A carbocation is an intermediate. So whenever you generate an intermediate, this is unstable. That is the rate determining step. And thereafter, you can see X is getting added here on this position. So this will be the major product. This is major product here. So I suppose all of you got an idea what is the mechanism happening here. Okay. Now if you compare the rate of reactions here, rate of reaction, it depends upon two factors. One is stability of carbocation. More is inward proportional to bond dissociation energy of HX. These are the two factors you need to notice. Clear? Now, if you may notice that there are two types of intermediates forming, intermediate 1 and intermediate 2. Now, these two intermediates, if you notice, in which H plus is getting added, this is a carbon which have two hydrogens. Now, if you add one more hydrogen, it will become richer, correct? So that's why if you notice here, for example, if you notice there is one hydrogen here and two hydrogens here to start with. So this is called unsymmetrical alkene. In an unsymmetrical alkene, this part is something which has a rich number of hydrogens, and the new hydrogen is adding on to the same position, correct? So if the hydrogen adds on to the rich position here and gets a carbocation on the poor position here, then we say it is following Markovnikov's rule. But if hydrogen is added on the poor side and positive charge is coming on the rich side of the carbon, then it is called following anti-Markovnikov's rule. So you can see, as per Markovnikov's rule, H plus gets added onto the richer side and X minus will get added onto the poor side of hydrogen. So this is where I can show you. This is the poor side. This is the rich side. Okay. And overall, if you notice, this two hydrogen has now become three hydrogen. So this rich part has become more richer. And this poor part is the one which is taking the X here. So that's how you end up getting this product. This is something which we call following Markovnikov's rule. But if it happens the other way around, it is called following anti-Markovnikov's rule. We say this is following anti-Markovnikov's rule. Electrophilic addition reaction. Now notice, earlier we learned that whenever we make elimination, it is endothermic because you are actually breaking stronger bonds to make a weaker bond. But it is the counter here. You are taking a weaker bond, breaking it and making a very stronger bond. Hence, all addition reactions are exothermic. Oh, this is exothermic. So these reactions are more favorable at a low temperature conditions and not very high temperature conditions. Okay. Now check this question here. Suppose if I add HCl to this one. Okay. Asha, first I forgot to mention that because it bond dissociation, it depends on bond dissociation energy also. The reactivity will be higher for HI, then HBr, then HCl. Okay. And it is far greater than HF. So HF will hardly make any reaction in this case. Okay. Now coming back to this questionnaire, when you have a pi bond, unsymmetrical pi bond here, as you add with HCl, by following Markovnikov's rule, H will get added here, chlorine will come. Now, instead of directly giving as H plus HCl, I have given it as H plus and then NaCl, which means first carbocation is forming and then Cl minus has been added. So eventually the product is the same in the first case or the second case. And then when you have HF, HF can provide small amount of H plus, which is enough. But F minus will be still very strongly held with other HF molecules. Therefore, F minus does not make a stronger impact here. So you first H gets added and the salt from the salt KCl, you will have sufficient Cl minus ions. So Cl minus will be present, that will be major. And fluorine having here will be in extremely trace level, traces. Correct? HBr, same role here. H will come here. Br will come here following Markovnikov's rule, that is major product. Now notice here, HI is a strong acid. So definitely I can expect this as H and I here. But at the same time, you have sufficient composition of Br minus also. And because you have enough Br minus will also attach here and you'll get this as Br. Okay. So we cannot say this one is major or this one is major. We can say both of them are significant, right? So both are significant amounts. Both are in significant. Sorry. Please follow. I suppose this is clear. Again, I have written rate here. So you note that HI is very strong, I mean, faster reacting than HBr, HCl, and HF. There is only one particular condition where anti-Markovnikov rule is followed. Here, anti-Markovnikov rule is more followed. That is when you take HBr in the presence of a peroxide. Either it could be alkyl peroxide or hydrogen peroxide and some heat. When you do that, then it will follow an anti-Markovnikov mechanism. Let me show you steps here. The first step is, you know that when it comes to an peroxy bonds are very weak. These bonds are very weak. So as soon as you heat or provide light, immediately it will break into radicals. And this step is called initiation. And in radicals, you know that there are always these steps: initiation, propagation, and termination. So first initiation will take place. And then the RO minus will react with HBr. And as it reacts, it will convert into ROH plus Br dot. Okay. So this is chain propagation. Chain propagation. And once you get Br dot, the Br dot is a very selective reagent, if you may recall. And when it is supplied to double bond, so what you will get is Br can add this way. Br will add onto this pi bond, making a dot here. Or it can add on this side of the pi bond. Br can add onto this side of the pi bond and make a dot here. These two are the possibilities. And you know that bromine always tried to give a more stable radical. And the first one is a more stable radical. Hence, this one is major, this one is major, and this one is minor. So this particular radical is major here. Okay, clear? Just for the clarification, as a note here only I'll give you. See, when it comes to Cl dot trying to react like this and getting into Cl dot here plus, you know, Cl dot like this, correct? This dot will be unstable. It will push back and try to make the reaction more in the backward direction. Okay. So that's why it is difficult to carry out chlorine's addition as compared to that of bromine's addition. And same goes with iodine also. I minus when it attacks here. So you will notice that I forming like this and I coming here. This is highly reversible. This is highly reversible. With chlorine, the reaction would happen, but the first step becomes difficult. The second step is very difficult for the chlorine part. So let me check that. Second step is difficult to proceed in forward direction. Proceed in forward direction. Because HCl bond is very strong, unlike HBr. So to break that and come into the forward direction, it becomes a challenge. So that's why the reaction mostly stays in the backward direction. That's why chlorine, iodine, both you may try, but they do not engage in giving away this radical form. And once you get this here, let me explain the complete mechanism here. So fourth step is, this is the stable radical. I'm directly writing for stable radical. Then again, it will react with HBr. As it reacts with HBr, H will come here and Br dot will go here. The same problem faces by chlorine as well. Even if the chlorine forms, let's say some amount of chlorine formed here. And if you expect this, sorry, HCl. Again, breaking H plus bond here with chlorine becomes difficult to get this HCl plus Cl dot. This is again highly reversible direction. This is also highly reversible direction. So because it is highly reversible direction, this chlorination is not very much observed as much as that of bromination. Okay. And what is major product here? This is major product. And on the major product, if you notice, the hydrogen is being added on the poor side and bromine is added to the rich side. And that's what is anti-Markovnikov rule is. So you can see here, anti-Markovnikov rule is being followed. Okay. And which means, suppose, take this example. If you have a pi bond here and you're trying to treat this with HCl, for instance, in the presence of peroxide, R2O2, and heat maybe. Because this is anyway reversible, it will not go as per R2O2's case. Instead, it will go with a normal carbocation formation. First, a carbocation will form, Cl minus will attack. So, it will follow only Markovnikov reaction. Follows Markovnikov's addition. Okay, it will follow Markov addition only. So, with peroxide or without peroxide does not make a difference in HCl. It only makes difference in HBr. Okay. So keeping that into mind, you can write the products here now. So if I give you HBr here, you know that this is a simple Markovnikov addition. So first a carbocation will form here, hydrogen gets added here, then bromine will add on to the carbocation. This is major product. While in the second case, first bromine will come here, radical will form here, and then bromine hydrogen will come here, and Br will be here. Correct. So this is anti-Markovnikov addition. HCl will have the same logic here, plus here, H here, and then on addition, you will get chlorine on this position. HCl with peroxide also, you will still have the same effect. Hence, you will get the same product in this case. Clear? So keep that in mind. HCl with peroxide or without peroxide gives Markovnikov addition only. So you can see these two are Markov. This is Markov, and this is anti-Markov. And DeMarco addition. Clear? See, let me put one JE question also. Okay. There was one more JE question that was asked on this time. Basically, if you have a double bond here like this, and you are treating this with uh, HBr in the presence of NaCl. Okay, sorry, uh, my mistake. It should have been Br. No, HCl only, HBr. Sorry. HBr in the presence of NaCl. Okay. And it is being asked what are the products that you can get. And these are all the products that were given. So we can have double bond is here like this. We can have products like you have to choose the more sensible major products. Correct. One product was given as Br here. One product was given as Br here. One product was given as Br here and Cl here. One product was given as Cl here, and one product was given as Cl here. Okay. So if the question is asked, what are the possible products? That means, okay, chances are it could form, but it may be major or minor. Okay. In that case, possible products, if the question is asked, see, possible products, which means there is a possibility that it may be major, minor, but definitely form. So you can see this is definitely forming as major. This is forming as minor. Chlorine can also form as major depending upon NaCl composition, and this can form as minor. So possible products are four. This one will never form. Correct. So if the question is asked, possible major products will be two. Which of them? This one and this one, which is following Markovnikov's rule. So answer is two in this case. Okay. Clear? Next. This is about hydrohalogenation. The next reaction is about halogenation itself. Halogenation, if you just try to go back to hydrohalogenation, we saw that there is a typical carbocation formation first, and then the nucleophile was attacking. While here, in this case, the carbocation is not completely formed here. Carbocation does not form completely, but there is a type of carbocation nature that is going to establish. So let's learn that first. Okay? Overall reaction is like this. When you have a pi bond, alkene, and you react with X2. X2 could be bromine, chlorine, or iodine in the presence of CCl4. So you will notice that X and X will get added on both sides. And this type of addition is called as electrophilic addition because you are adding electrophile first. One is nucleophile. Out of this X, one is nucleophile, one is electrophile. But whichever you are adding in the rate determining step, that becomes the name of the reaction. And in the rate determining step, we are adding electrophile. And once the two halogens are adjacent to each other, we call it as Wick dihalides or vicinal dihalides. Okay. Now let's notice the mechanism steps here. What is the mechanism steps which we can notice here? Check. First one. The first step is the pi bond which is present here like this. Let it react with X2 in a non-polar solvent. So you might ask, sir, why non-polar? See, this is highly non-polar. To make sure this dissolves, we require a non-polar solvent. So you can take CCl4, you can take CS2, benzene, any of these cases, it will make an addition here. Now notice the pi bond will attack here. The pi will attack on this X and this X is being lost out. So how does the reaction take place here? So first on this pi bond, one X got added here this way and that will get positive charge and the other X has released as minus charge. Halonium, halonium bridge intermediate. So we got a halonium bridge intermediate here. And the next step, the second step is once we get a see before second step, let me show you what are the resonating structures here. Because it has a positive charge, you can expect this will break a bond once on this end, you get a positive charge. And it can break a bond on this end, it will get a positive charge here, which means these two carbons will also show some positive charge due to the resonance effect. So if I write the hybrid for these three, I can say this will carry some delta positive. Here you will have delta positive. Here you will have delta positive. And once you have this delta positive charge on it, we have X plus delta positive. This has some delta positive and this has some delta positive. Now the nucleophile, in the solution, the nucleophile which is left is only X minus. So this X minus could attack. Now X minus could attack on both sides. It can attack on this end, it can attack on this end, and that's how it can break the bond between carbon and this halogen here or carbon and halogen here. You can break it on either side. So as it breaks down, so what do I get? You will get X here, correct? And this X coming on this position. Let me show you with colors. If this is the X we are talking about, I'm saying that X is here, while this X minus is present here, this way. This is one product I can have, or the other product is very similar to that, correct? Where we have X and X, but this time uh, this X is here and this X is here. These are the two possibilities. Now I need to figure out which one is major in this case. Okay. Now tell me about this point once. See, in the resonating structures, you can see there is a positive charge forming here and positive charge forming here, which means if you compare these two resonating structures, right? Let's say this is intermediate 1 and intermediate 2. So we can say that stability wise, if you compare intermediate 1 is more stable than intermediate 2, which means molecule will have more of this nature than this nature, right? This intermediate nature will be less contributing, but this intermediate nature will be more contributing. So if this is more contributing in the hybrid structure, I can say that when these two carbons are connected to halogen like this with delta positive and delta positive, this one which has, this one which has, let's say, X bond length, and this one which has Y bond length, I can say that the bond length wise, X is larger than bond length of Y. For simple reason, breaking this bond is easier because that's how you can get this intermediate. Okay. So if this bond length is larger, then bond energy required is lesser. So bond energy is required in this case is lesser. X required is lesser. Hence, nucleophile will always decide to attack here because breaking of bond is much easier here. So therefore, nucleophile will always attack on more substituted carbon side. It will attack more substituted carbon side and simultaneously break the bond. Got it? Now notice this carefully. When it is attacking, let's say here, X is present with a plus charge. And you know that nucleophile, in this case, the nucleophile is X minus. So X minus basically is attacking from this end, which is major, and this will break here like this. So we will have, notice one thing. This is the X which you are getting, and this is the X which you are getting, correct? Color wise, if you notice, this is the X, this is the X, and this X minus and X minus is same. Because three-membered ring is a planar substance. Okay, it is planar. Three-membered ring means it is planar. So in a planar molecule, this X minus cannot approach from this direction because I need to break this bond. It has to always approach from the opposite direction so that it can hit onto the sigma star orbital and break this bond. Therefore, the bond breaking and the bond making are opposite to each other. Hence, this is an anti-addition. It is an anti-addition. So remember, halogenation is an anti-addition in this case. And this is major product. This is major product. Please do let me know anybody has a doubt in understanding the mechanism. I'll discuss again. Recording in progress. Type of reaction. Now see the second type of reaction where hydration is happening is oxymercuration and demercuration. Okay, just a second. Please check oxymercuration and demercuration. So basically we have first step, not even first step, I would say HgOAc twice will exist in equilibrium as HgOAc plus ACO minus. This is like the zeroth step, you can say. Correct? And then the first step would be the pi bond which is there will try to attack on Hg plus OAc which is present in the solution. Acha, OAc means what? AC means acetate, this one. CH3C double bond is AC. So as soon as this happens, the pi bond will attack on mercury and you will see a three-membered ring will be formed as Hg, OAc here, and bonding will be forming here with a positive charge on it. Got it? And ACO minus usually ionizes from here. So therefore, we will have this double bond here with mercury 2 plus and ACO minus. Now this is the 2 plus form which you have. This is a three-membered ring. And on here, water as a nucleophile will attack. Earlier we learned that Whenever you have a positive charge on this three-membered ring, the attack would usually happen on the more substituted kind. That's why the attack of water will make on more substituted kind, breaking this bond. So as it happens here, so you will see that water has attached here OH2 plus and mercury is present here as Hg plus. And from here, H plus is being lost and we will get mercury Hg plus and here we'll get OH. This is the next intermediate which you get. And then the third one, up to the first two step, it is, oxymercuration. That means mercuration is happening. See what I'm saying? The first two steps is where the mercuration is happening. And the next step is where demercuration will take place, which means we have BH4 here. I'll write this way, BHH with minus charge on it. Got it? So what will mercury do? Mercury will try to take away electrons from here. Okay, because uh, it will try to deposit itself as a mercury precipitate. So in that case, the H minus from here will attack and H minus will attack and BH3 will be separated. So what do I get from here? So I will get, you will notice that OH is present here, correct? Sorry, bond is not breaking from this side here, like this. Mercury is leaving from here and therefore H minus will attack on this carbon position. Second, let me write the arrows correctly. On this carbon, right? See, the H minus would attack on this position, removing out this mercury. So what do I get? I will have hydrogen here and OH here. Mercury got deposited and BH3 has left. Okay, so you can see this hydrogen got added onto this position. This is the overall reaction. So I can, let me write on that. The step one and two are called oxymercuration steps, where mercuration is happening. While step three is called demercuration step. Step three is demercuration step. Please notice this, everybody. Make a note. See, here there is one thing you should realize. When mercury was adding here, this step where mercury got added onto this double bond position, it added from the same direction. So here I can say the first step is syn addition. This is definitely syn addition. That is oxymercuration. Oxymercuration. Here it is an electrophile, and that will be a rate determining step, a slow step, and it will make a syn addition. Thereafter, water which is adding here and bond breaking here is an anti-addition. This step is an anti-addition. And thereafter, the last step, when you check out on the last step, have you noticed this single bond? This single bond can rotate on any directions, isn't it? Clear? So which means this H minus can attack from here, or it can attack from here. It does not make any difference. And around the single ball it is moving. So I cannot say that the final product is only coming from erythroform or a thrioform. It could be any of that. So that's why now this time it is a non-stereo, non-stereo specific addition. So that means the overall addition is non-stereo specific, everybody. The overall addition of water is non-stereo specific. And secondly, if you may have noticed, correct, we are not getting a complete carbocation. So that's what we earlier emphasized. So no carbocation, and no rearrangement. No rearrangement observed. So only direct addition on that delta positive carbon, correct? So no carbocation, no rearrangement observed in this case. And we found that it is non-stereo specific. And most important, the last addition which you have noticed, right? The H and OH are appearing as if H is on the rich side, OH is on the poor side, which means it is a Markovnikov addition, which means it is following Markovnikov addition. It is following Markovnikov addition. Right. Everybody look into this case. So these are the important pointers that you need to learn from oxymercuration and demercuration. The next reaction type is called hydroboration oxidation. Hydroboration oxidation is where we are using B2H6 this time. We are using B2H6. So let me show you how, step by step. Again, like a zeroth step, let me show. We have B2H6 diborane. Diborane, when you react with, or rather add it to THF, this is tetrahydrofuran. This is the solvent. As you add to this solvent, the solvent will take have lone pair on it, so that will attach on one part of the boron, and the other part of the boron will release. The released boron is what acts like an electrophile. So this is the electrophile. And I hope you understood the reason why THF is used. The solvent is used to generate the electrophile. So now the electrophile has been generated. So this electrophile is also a Lewis acid because it has an empty orbital. Now let's start with the first step. The first step is we have a pi bond here, and you're treating that with BH3, which has an empty orbital. Okay. So what would happen here is the pi bond will try to feed onto the empty orbital, and this hydride will try to feed onto the carbon, which is becoming slightly positive. And that way you will notice a four-membered ring is formed here. So like this, you will have a double bond breaking, a bond with boron making, and hydrogen attaching, which is breaking from boron. Other two hydrogens are intact like this. This is the way it is forming a four-membered cyclic transition state. So we call it as 4-MCTS. So through this transition state, it is forming a compound like this, where you have hydrogen here, and BH2 here. Hydrogen and BH2 here. Now you can see hydrogen and boron got added from the same direction. So it is what type of addition? Syn addition. So the first step is a syn addition here, where hydrogen and boron are being added. Second, what we didn't realize here is that the boron which you have added here now, so we got this as BH2, it has again become an empty orbital to which the next mole of pi bond, the second mole of pi bond will try to feed onto it. It will attack, hydrogen will attack back. So as this to and fro happens, now this time you will get boron with another alkyl group and hydrogen. So this time we have two alkyl groups and one hydrogen on the boron. So we would get this form. And this, when you react with the third mole here like this, so the pi bond from here can be attached like this here, and hydrogen can be attached to this position. So 3 moles you will get here this way. Boron like this way. So there are 3 alkyl groups which are, now there are no more hydrogen. So it will stop here. So this will become tri-alkyl boron or borane. Tri-alkyl borane, which we can write it as R3B. So 3 moles of alkyl group will be formed here. Okay. Now see the fourth step is once you have this boron, let me write this as R with boron connected and R with boron connected. And I'll show this one just for our understanding. I'll show this one. This is how the compound was. This is also an R group. I'm just showing it for a purpose of how the reaction takes place. Check. Once you have it here, in the presence of peroxide and OH minus, correct? In the presence of peroxide and OH minus, you will notice that 3 moles of ROH will be formed and 1 mole of BO3 minus. BO3 3 minus will be formed. This is the overall reaction that will take place. Correct? So how does this happen? See, first H2O2 in the presence of OH minus. H2O2 is a weak acid. So that weak acid will take OH minus and convert itself into uh, H2O plus HOO minus. One H plus has gone from peroxide, you'll have HOO minus. So this HOO minus, where you have this as R group, R, boron, R, and we have structure like this. Sorry, we have structure like this here. Now what happens here is HO minus, O and H. This O minus will be able to attack here, and as it attacks as a nucleophile, it will attack. So you will have boron here, R, and this way it is present. And now we will have this as O, O, and H. We will see this as O, O, and H formation. Okay. Now, as we have this OH, you know that oxygen-oxygen bond is very weaker. So because of the weaker bond, now this carbon will take the electrons and try to attack on this carbon, this oxygen, and this oxygen will try to take away electrons. And that way, you will notice that we have R, B, R with O minus, and on the other side, we got an alcohol. Okay, we got H was already added. Now OH is getting added. So you will get this part again reacted with 2 more moles of O minus OH. It will give us 2 more moles of two more moles of this product, H and OH, and eventually boron will become BO3, 3 minus. So totally we have 3 moles of alcohols, primary alcohols. Now if you notice the final product here, like this we have H is here and OH is here. So see the addition kind. Addition kind is it is following anti-Markovnikov addition rule. Following anti-Markov addition rule. And see if bond has to break here and this has to attach, all of them should be on the same plane. That means here this group going and this group going makes the final carbon getting attached here and boron here will be on the same side. So overall I can say it is a syn addition. Overall it is a syn addition. So it is highly syn stereospecific. So the important pointers here. So again, no carbocation, no carbocation. You will see no rearrangement, no rearrangement, but it follows anti-Markovnikov rule. Follows anti-Markovnikov rule. Okay. So that way you will get this as an alcohol part. Anti-Markov. Got it? Let me show you with an example. Sorry, I forgot to mention the stereospecificity. Okay. Overall reaction is overall reaction is syn stereo specific, which means HOH added from same side. Overall, eventually you notice that H and OH are from the same place only. Okay, let me put one example here. Suppose I have a double bond like this, and then I'm treating this with B2, D6, H2, O2, and OH minus. You know that the deuterium gets added always onto the more substituted kind. So that means if this methyl is coming out of the plane, I can say the deuterium can be here. And the OH also has to be on the same. That is what we was in uh, addition. So here, if you have deuterium, be here and D and OH are on the same side here also. Because it is like chiral set, it is like the mirror images of these two. So I can say 1 and 2. So 1 and 2 are enantiomers. 1 and 2 are enantiomers and forms racemic mixture. Okay. So everybody, please go through step by step once again. Check whether you understood any. I mean, if there is any point you need some explanation, check out the first three steps. So you see the first one, D3O plus. So what do I get? You will know that first D will come here and thereafter OD will attach on the most stable position. This is the most stable position. So OD will come here. So that means it is following carbocation, rearrangement, Markovnikov and not anti-Markovnikov. Second one is oxymercuration, demercuration. So it will be like this. No carbocation, but hydrogen will come here and deuterium will come here. Sorry, OD will come here. That is following Markovnikov's rule. Okay, because this actually hydrogen comes from H minus here. Just try if you recall. And water is the one which will attach on the more substituted position. So OD will come there. So no carbocation, no rearrangement, only Markovnikov follow. Next. In this case, same oxymercuration, demercuration. OH is coming here and deuterium is coming on this position. So these two is not the case, and here Marganikov is followed. Next. D2H6. In D2H6, you know that it is anti-Marganikov, which means deuterium will come at this position. Okay, deuterium will come at this position. Clear? And OD will come on the other position. Okay, just a second. See, then D will come here, and thereafter we will get OH on this position. No carbocation, no Markovnikov, only anti-Markovnikov. And lastly, you will have hydrogen here and OD here, right? Because this time D2 OD is there. I mean, you can see OD minus means OD will come. Here, hydrogen is there means hydrogen will come at this position. So, therefore, no carbocation, no rearrangement. What it is following anti-Markovnikov. Please check your answers. This is what you should get. Done. Next is hydroxylation reaction. Hydroxylation is addition of two OH groups. And two OH groups can be added by majorly these three reagents. One is alkaline KMnO4 in a cold condition, osmium tetroxide, with sodium hydrogen sulfide, slightly mild acidic condition, and then peroxy acid. This is peroxybenzoic acid followed by acidic hydrolysis or basic hydrolysis. These three reagents, wherever you notice with a double bond, you are expecting them to add with two OH groups. And when you have alkaline KMnO4, it is basically a syn addition. It is a syn addition here. While osmium tetroxide is also a syn addition. And in this case, it is going to be trans addition. Trans addition. So when you want to trans addition, sorry, not trans, I mean anti addition. If you want an anti addition, then you will use the peroxy acid. If you want a syn addition, you will use any of these two. Okay. Here. Now we know how it operates. Let's see, based on the products, how do we need to write it? Here, more than mechanism, you need to learn about how the products need to be represented. So let me put this as an example. Suppose I have a cis molecule here and it was given what will be the product in case if you have an alkaline, okay, cold and dilute, sorry, alkaline cold dilute 1% KMnO4, 1% KMnO4. So when you have dilute at 1% KMnO4, it meant that we are using very dilute KMnO4, which makes it this makes it something called Bayer's reagent. That's the name of this reagent. So it is exclusively used for syn hydroxylation. Syn hydroxylation. That means syn addition of two OH groups. You know that cis, when you make a syn addition, you should get erythro. So the product should be erythro. So you can write it like this. So product is this way with two methyl groups and two OH groups. and with two H groups. In fact, you can get the same structure in a mirror image, but unfortunately, in this case, because both sides we have methyl above and below, it would become it will become a mesoform and identical uh, atom. So here there is a plane of symmetry, here there is a plane of symmetry. So this is meso and this is meso and identical. These two are identical. Okay. So in this particular area, you are supposed to know more of this kind. Now, what is happening to the manganese on the other hand? See, KMnO4 is actually a purple pink color, purple pink solution. Since it is a purple pink solution, after the reaction, it will turn out to be MnO2, which is a black brown precipitate, black brown PPT. Okay, so there are two things to learn from here. One, oxidation state changes from +7 to +4 for for manganese. This is the second. This is the first part of it. Second, the color, I mean, the solution will become colorless. Only this will become precipitate, but the rest of the solution becomes colorless. Hence, we can use this as, okay, detection of, it can be used for detection of unsaturation, detection of unsaturation as pink color gets decolorized, as pink color gets decolorized, pink color get decolorized. Okay. So this is what you will have it in the cis form. Now, notice the trans form of it. You have a double bond here, example. And that when you treat with PHCO3H and it makes an anti-addition here. PHCO3H means it is benzene peroxy acid, like this. I have basically benzene and C double bond O, OOH. This is peroxybenzoic acid. So this is peroxybenzoic acid. And when you have peroxybenzoic acid, the first step would be about getting an oxygen on it, like this. Oxygen will come on this. Okay. So it is forming an ether type, right? Cyclic ether, or this is called epoxide. So hence it is called syn epoxidation happening. The reaction is syn epoxidation. So the first step is syn epoxidation. And once you get an epoxide here, and that's when the hydrolysis is taking place. That's when the hydrolysis is taking place. And through hydrolysis, you will see both of them, you will get the OH on both sides here now, like this. You'll get OH and OH here. Got it? Now, overall reaction of H3O here is an anti-addition here. Okay, overall is anti. Here, acha, this step I'll write down as syn because I have not written the overall reaction. Now, this step is anti. Therefore, if you write the overall reaction like this trans plus pH CO3H, and that is followed by H3O plus, let's say, if at all it is given this way, then you will have like this. And now you will have OH here because you are taking a trans form and overall making an anti-addition. So trans plus and anti will make it again meso. So you still have this meso form. So what I'll do, just to differentiate, I'll put this as phenyl here and methyl here. Phenyl here methyl here, phenyl and methyl. So above I'll put it as phenyl and here as methyl. So you would see that this will still have a this will still have a mirror image possibility. Hence, we would have HO and HO here, H and H. So you will see a plane of symmetry passing through it. Sorry, plane of symmetry is not there in this case. So therefore it is. And since there is no plane of symmetry, these two are enantiomers of each other, 1 and 2. So I can say 1 and 2 are enantiomers. 1 and 2 are enantiomers and show and form racemic mixture. Form racemic mixture. Okay. So this is the overall reaction, everybody. So please make a note of it. Check both the reactions quickly. Make a note. Right. Sorry. Check. I told you that here it is forming MnO2, while in this case it will form H2 H2OSO4. So oxidation is correct. So remember here osmium will have +8 to +6 oxidation state. Okay. And first these two are syn additions and this will make an anti-addition. Let me put a last question here. The last one is, suppose if you have a double bond at this position and you have a double bond at this position and you are using only one equivalent of peroxy group, one equivalent, then addition usually happens on the more substituted side because like this is major product. Reason being, the nascent oxygen, I mean, the single oxygen is going like an electrophile. So electrophile will always add onto the position where the double bond has some support of alkyl groups. So therefore, so let me write on the reason. Peroxy acid, peroxy oxygen is almost like an almost like an electrophile. Electrophile. Hence, more supporting pi bonds. Pi bonds makes first attack. Make the first attack. Done. So this is all about the addition reactions, everybody. This is the last part. Clear? So this is the second part of alkenes done. The last part of alkenes is about oxidation reactions, all about various forms of oxidation reactions that include ozonolysis, KMnO4, and some other few more reactions, one or two here and there. And then we can start with alkynes. But the major part of alkenes, as per your syllabus, what is there?